Here's a demo of our research, visual proximity-based video decolorization via temporal coherent optimization. Video decolorization has its unique value in some specific fields, but recent papers always put emphasis on image decolorization. It is true that a video can be regarded as an image set, and to some extent image decolorization method can be applied to video decolorization. But a video has some unique properties that an image set does not have. First, the frames of a video always share a similar content. As the sample shows, all of the 4 video frames are about a man in blue with red background. However, the above image set does not have this property. Second, the video frames are established on a time shaft. In other words, you can say frame 2 is adjacent to frame 1. But it is meaningless to say image 2 is beside image 1. These 2 properties of the video are often neglected by researchers implementing video decolorization. To show the defect of neglecting the internal relationship between video frames, here is a comparison between Mark Grundland's result and our result. Notice that the 2 input frames are almost same. However, in Mark Grundland's result, we can see evident difference of luminance. This will cause visual flicker problem. To avoid this problem, we need to promise that in the adjacent frames the same color should be converted into the same grayscale, so that the luminance will seem as coherent and the video can be viewed smoothly. Here's the overview of our algorithm. Before we convert one frame into grayscale, we compare it with the previous frame and calculate the decolorization proximity, which is based on image entropy. The higher the value is, the more similar these 2 frames are. Then the decolorization proximity will be regarded as a criterion for DC-GMM classifier to determine the specific method of decolorization. There are 3 decolorization methods can be selected, which use differential refinement, coherence refinement and optimized C2 grams correspondingly. In general, our method uses the decolorization proximity values as features of DC-GMM classifier to determine the specific decolorization method for each frame from alternative methods. Inspired by Gaussian mixture model, which is an effective unsupervised classifier, we define the DC-GMM classifier for particular use in videos. It can classify pairs of neighboring frames into 3 clusters in order to select the decolorization methods. The probability function includes Gaussian term and penalty term. Compared with using 3 decolorization methods uniformly, repeatedly using the high proximity decolorization method will lead to loss of video quality, and continuous use of low proximity decolorization method will cause high time cost. To avoid this defect, we add penalty term to likelihood when DC-GMM classifiers successively put data points into one cluster. To find a well-defined function form of the penalty, it is expected to allow a relatively small number of successive data points assigned to one cluster, while giving definite penalty when this number increases to a specific upper bound. By DC-GMM classifier, the specific method of decolorization is determined. They are high proximity decolorization, HPD, median proximity decolorization, MPD, and low proximity decolorization, LPD. We will introduce them one by one. According to classification results of the DC-GMM classifier, the color frame with similar content to previous frame will apply high proximity decolorization method. In this case, we reuse the grayscale result of the previous frame and adjust it by differential refinement frame, which is based on optical flow algorithm. High proximity decolorization method can greatly reduce the redundant time of redecolorizing a high similar frame. Compared with high proximity decolorization method, color frame shows a bit larger difference within the case of median proximity decolorization method. To keep time efficiency, reutilization of the previous grayscale result is still acceptable, but may lose some details in current frame. To bridge the difference between adjacent frames and smooth the luminance change, temporal coherent work is necessary. We define the result got by this work as coherence refinement frame, and the final grayscale result is the weight sum of the previous gray frame and the coherence refinement frame. Frames of low proximity infer the content has changed a lot. The current frame should be regarded as a totally new image never been processed before. Therefore, any result of the former frame is useless. We define an energy function which has two terms. The first term is called ES, which represents the energy of a single frame. The second term is called ET, which represents the coherence with the previous frame. And total energy E combines ES and ET together. The less value of E represents the better quality of the grayscale video. To minimize E, we use conjugate gradient method. To show our result, here is the input color video and its grayscale result. To show the time efficiency of our algorithm, here is a line charts of decolorization time. The green curve shows the decolorization time per frame processed by Grandland's paper, which implements decolorization frame by frame, while the blue curve illustrates the decolorization time per frame obtained by our solution, alternatively applying high, median and low proximity decolorization methods. Benefit from the high efficiency of high and median decolorization methods. Our solution framework uses much less time than Grandland's solution. To show the performance in quality preserving, we compare our result with Kim's result. In Kim's result, it loses color contrast and cannot discriminate the silver and blue color in the input frame. The result proposed by our paper is much better. Besides, to show the performance in coherence preserving, we compare our result with Grandland's result. In Grandland's result, the same color in different frames is wrongly converted into different grayscale values, which leads to color inconsistence. In contrast, the result produced by this paper has a much better performance in preserving the color consistency in adjacent frames. Here are the references mentioned in the demo. Thank you.